Welcome back, everybody. So we finished with completeness. We finished everything. So we have now a deduction system to produce formal proofs, like very syntactical, just based on symbols, manipulation of symbols, formal proofs that is complete. So if something can be proved or should be proved, then it can be proved. So if something is true in terms of models and satisfiability, then it can be proved. So the logical axioms that we set, that set big lambda that we had for the set of logical axioms is complete. There is nothing else that we need. Modus ponens and the logical axioms give us everything. As you tried, as you saw, it's very tedious to do a proof in that system, but that's enough. I mean, yeah, we can prove meta theorems and stuff to make it less tedious to prove things in there, but that's enough. So if you write a proof, you should be able to write it in that, even though it might drive you crazy. There are computers now that allow you to help you write formal proofs. They help you with all those meta theorems and to transform one proof into another, and then you might end up with a long formal proof, and the computers can just go and check one by one that every line is correct and confirm that the proof is fully correct. Though mathematics, we still just do proofs in English with paper and pen and have other humans to check because that's too tedious to do. But okay, but such a system exists. That's the important part that we prove. Before that, in the course, we mostly concentrated on the formal system in the last 4 weeks. And before that, we were talking about first order logic and the language. And the language for first order logic is very good. As we saw, we are able to play with it quite a bit, but it has a lot of limitations. And we concentrated a lot of many weeks on the study of these limitations. What are the limitations of first order logic? And essentially, using compactness, which was an important tool, we were able to show some of these limitations, things that are not definable, classes of structures that are not elementary. So we saw a lot of things that we couldn't do in first order logic, essentially because the language is not that comprehensive. And we pay a lot of attention to that. So that was our way of understanding what is, how good is first order logic and what you can do with it and how does it work, the combinatorics of first order logic. But so it's not complete. We saw that it's lacking a lot of things, but that's because the setting that we were looking at, right? We were looking at graphs and we were in a setting like we can only talk about S relation and you couldn't talk about connectedness, for instance. But if you look at the right setting, if your interest is to be complete in the terms of being able to talk about all of mathematics, then if you look in the right setting, the language is complete. So you can find the right settings, for instance, set theory, in which there's a list of axioms called ZFZ, Zermelo-Fraenkel choice, over a vocabulary that only has one binary relation symbol that belongs. That's it. But those axioms kind of define a setting, the universal set, where you can talk about everything in mathematics. There, like everything that is done in like all your undergrad years of mathematics and possibly all your grad years, unless you're doing logic, can be developed there. There are some things that are not. That's why I say essentially it's not everything they can prove there, but it's pretty good. And in that case, it's obvious that the language is complete. That everything you want to say in mathematics, you can say it in by a first order formula, like the ones we saw. So not only the formal system is complete, and like if you want to know more about that, you should take 136 at some point next year. That's a great course where you can see how that theory is developed. And then came Gödel in the 1930s. After he showed completeness, like a few years after, maybe 5 years after, he showed the incompleteness theorem. But now he was referring to the axioms, in the case when you're trying to develop all of mathematics. And he proved that if gamma is a consistent set of axioms, set of sentences, that contains enough of arithmetic. So the vocabulary could be anything, but at least it contains 0, 1 plus times. and it should just have the basic properties of arithmetic about 0 plus 1 plus some times, just the basic ones, some minimal to be able to work with it. Then, and it has this property that is computably enumerable, which is, I guess, is important to have, because if you have an infinite list of axioms, you want to know that at least you can recognize them. So computable in that sense, that you can, at least if you see it, I don't know, you can put it in a computer, and the computer can tell you, yes, it's an axiom, no, it's not an axiom. If you don't have that, then it's pretty useful if you don't even know what's an axiom and what's not an axiom. So the assumption is that there has to be at least a computer that can enumerate one by one all the axioms in your list. So if you have this consistent, contains enough arithmetic, and is computer enumerable, it cannot be maximal. So it cannot contain everything and its negation. And actually, if a set of axioms is computably enumerable, then you look at all the theorems that it proves, they're still computably enumerable. So, like, this is saying that if your set of axioms is computably enumerable, there's always going to be a formula, a sentence, that neither it nor its negation are provable. So that is missing. You cannot prove either it or the negation, so you cannot decide which one is the true one. There's always going to be something missing, and therefore your set of axioms is incomplete. It's not proving everything. There are some sentences that you cannot decide whether they're true or false if you just restrict yourself to probability. So that one, if you want to know about that one, okay, so sorry, that one is 136. This is 135. Those are the courses you should take. That's where you would see the proof of these. So it's pretty interesting, pretty wild. So yes, so far we now can understand what Gödel completeness says. There is something you can prove, and I hope you guys enjoy all these videos. They did take some work, but I hope made things clear, and see you guys later.